Welcome back. Okay, so in lecture 24, now that we know about templates, we're ready to talk about a couple of so-called container classes that the C++ standard library provides, namely the vector of t container and the set of t container. Altogether, there are about 15 or so standard containers, that is, standard data structures, that you can use to store integers, characters, strings, what have you. And we're going to look at these two specific examples, vector and set. We're also going to talk about how to use something called a range for loop to step through all of the items that a container contains within it. Also, we're going to introduce the auto keyword, which you can use as a shorthand for typing out, or to avoid typing out, complicated data type declarations. We're also going to talk about iterators, which are a special kind of pointer-like class that you can use to step through items in a container, not only a vector or a set, but the other standard containers in the standard library. And you can also use iterators to step through things like ordinary arrays and string objects as well. Okay, so what is a vector t? Well, t is a data type. Vector is parameterized on a data type. So you can have a vector of int, a vector of char, a vector of double. You can have a vector of pointer to employee constant. You can have a vector of pretty much anything that can be copied. It's basically an improved version of an ordinary array of t. Now, when you declare an array of some type, like C is an array of 5 char, that array is of fixed size. A vector, on the other hand, is a flexible size. Internally, it uses dynamic memory allocation to grow and shrink the size of the contained sequence of values. Fortunately, because the vector t is so carefully written, you don't really have to know or care about the internal details of that dynamic allocation. We can find out about how large the vector is. We can grow it, shrink it. We can store, or I should say, values are stored, just like arrays, in ascending contiguous memory locations. So given a vector, we can find out the address of the sub-0 item in the vector, and we know that the sub-1 item and the sub-2 item and sub-3 item and so forth are in ascending contiguous locations, just like in an ordinary array, up to the last element contained within the vector. We have a variety of initialization mechanisms, a variety of constructors available for the vector class. We have assignment and equality and inequality test, as well as relational test operators defined for vectors. We can do subscripting on vectors with square brackets, just like we can on ordinary arrays. And we also have these things called iterators that we'll talk about shortly, that allow you to step through the items in a vector and also apply standard algorithms that are part of the standard library to a vector. And we have a bunch of member functions we can use for inserting values into vectors, removing values from vectors, replacing values in vectors, etc. So here's our first bit of vector code. This is in an example code file called vectortest.cpp that you can have a look at. And on slide 3, I'm simply demonstrating several ways, but even so, there are even more ways. But here are several ways of declaring and initializing vector objects. Each of these objects that I'm declaring here, IV, IV2, IV3, IV4, and IV5, is of type vector of int. Notice that we use the angle brackets here, and we put the data type that we want to store within the vector in those angle brackets. So the angle brackets indicate that this is a template being used. When I say IV is a vector of int and I don't provide any initialization information, I automatically get a correctly initialized empty vector. On the other hand, if I give a positive number in parentheses, that number is interpreted to be the size of the vector that I want, and by default, all the values in that allocated vector of int are going to be set to 0. So here IV2 is a vector of int of size 4 filled with zeros. If I provide a second number in parentheses, then that's taken to be the value that I want to have those that number of values set to. So IV3 is a vector of int with 4 7 values in it. In curly braces, I can just specify a list of values as I could with an ordinary array. In this case, I'm going to end up with IV4 containing, being a vector of int containing 6 values, 1, 2, 3, 9, 8, and 7 in that order. Assignment is well defined, so IV started out as an empty vector. If I say IV gets IV4, now IV is a copy of IV4. Okay, so if I were to look inside of IV4, I'd discover 1, 2, 3, 9, 8, 7, the same values that are in. I think I made a mistake. If I were to look inside of IV, I would see the same sequence of values that I have in IV4. And finally, on slide 3, here is an example of the copy constructor being used for a vector of int. IV5 is a vector of int initialized as a copy of IV. Well, because IV now contains a copy of IV4, IV5 is also going to contain a copy of those same values. All right. So here's the first of many example operators and member functions we can use with vectors. Vectors are compared for equality and inequality and ordering in the same way that string objects are compared. That is, we compare elements, one element at a time, to see whether the two vectors are equal or not equal, or in this case, we're trying to test whether IV2 is less than IV4, and next IV3 is greater than IV4. Well, let's have a look at IV2. IV2 is a vector of 4 zeros. IV4 is a vector of 6 elements, and the first element is 1. So we discover almost immediately that IV2 is less than IV4 based on this element-by-element comparison, because the initial item, the initial value in the initial element in IV2 is 0. The initial element in IV4 is a 1, and because 0 is less than 1, we report that IV2 is in fact less than IV4. On the other hand, IV3 has 4 7s in it, and because the first element 7 is greater than the first element 1 in IV4, we get reported that IV3 is greater than IV4. Now, we can get into an argument about whether this makes sense to compare vectors this way, but this is how this comparison is implemented. We compare on an element-by-element basis. Next, we're going to use something called a range for loop, which is sort of like a simplified for loop that's very convenient, very concise notation if you want to step through all of the elements in some kind of container. So rather than using the 2 semicolons with the initialization, test, and change part, I don't really have a test in this version of the for loop. I just specify the declaration of some loop variable to be of the data type of the elements contained within the container. In this case, IV is a vector of int That means each element is going to be an int. And this simply says to loop through all of the elements in IV, assigning each element one by one to this int loop variable called EL, EL for element, okay? So here EL is going to contain a copy of the sub-zero element of IV initially, and when we display that followed by a space, what comes out is a 1 followed by a space. Then the next iteration through, EL takes on the value of IV sub 1. The second element in IV is 2, so we get a 2 and a space displayed. And then 3, 9, 8, 7. And when we run out of elements in that 6-element, I keep saying array, I mean vector. When we run out of elements in that 6-element vector, the loop simply ends. And following the loop and the cout of the elements, I have one new line character being displayed, so we drop down to the next line. Okay. This next range for loop is similar but also different in a very important way. Notice the ampersand here following the data type of the loop vector, the loop variable. So EL this time is a reference to an int. Consequently, as this range for loop goes through the elements of IV, I'm going to obtain a reference to each element one at a time. So first EL is set to a reference to IV sub 0, and I'm saying that element times gets 2. All right, so the elements in IV were 1, 2, 3, 9, 8, 7. And this red range for loop is going to modify all of those elements to 2, 4, 6, 18, 16, 14. Okay, so we can, by using a reference loop variable, modify the elements contained within this vector. And then I have another range for loop here that just redisplays the elements in the vector. This time they're double what they used to be. Okay, so you can compile and try out this vector test code file for yourself. Here's the output that I get from the code on slide 4. We do get told that IV2 is less than IV4. And then on the next line, we'd get told that IV3 is greater than IV4. Then the blue range for loop displays the original, the current contents of IV. Originally, IV was empty, but then we assigned a copy of IV4 into it. All right, so IV at the point of the blue range for loop is 1, 2, 3, 9, 8, 7. Then in the red range for loop, we're doubling each element, so that in the green for loop, we see that it's now containing 2, 4, 6, 18, 16, 14. Okay. So here's a bit more detail about this idea of a range for loop. A range for loop is a very convenient mechanism if you want to simply iterate through all of the elements contained in some kind of container. And containers include not only vectors, such as the examples that we just looked at, but also ordinary arrays can be treated as containers for range for loops to step through. A string object can be thought of as a container of a sequence of char values, and we can use a range for loop to step through those. We also have set, which is a standard library container type that we're going to look at toward the end of this lecture. And we have a ton of other container types in the C++ standard library. We have lists, we have double-ended queues, we have maps, we have hash tables, which are called unordered sets. Altogether, as I said, there's about 15 C++ standard library template container classes. And as we showed in the last two range for loops on slide 4, we can either loop through copies of values within the containers, or we can loop through references to the values in the containers. Here's an example in which we're using an ordinary int array, AI, excuse me. I'll get this right. A1. So A1 is an array of int initialized with 6 int values. And because the array is locally defined and the compiler knows that A1 is the name of an array, I can use a range for loop to step through and access each of the elements of A1 one at a time. Here I have A2 specified as an array of 5 doubles. I've given 3 initial values for A2, pi out to 4 decimal points, e out to 4 places, and then 1.0. Remember that by default, I'm also going to have 2 0.0s to complete the initialization of the 5 elements in this array of doubles called A2. And now I'm using a double loop variable to step through and display each value from A2. Just as a trivial matter, remember that if the value of the double has 0 as its fraction part, then in the default notation, the trailing 0 is not displayed and neither is the decimal point. This is, obviously quite inconsistent with Python. So these 5 doubles in the array A2 come out as 3.1416, 2.7183, and then 100 as the trailing 3 values. Now, here we have, this is a little bit of a tricky one. A3 is an array of char, and I'm initializing that array of char using a string literal hello. So the first question for me to ask, which I'll also have to answer since you're not here, is how big is this array? Well, remember that when you write a string literal, there is a null character on the end. So A3 here is actually an array of 6 char, H-E-L-L-O and null. I'm using nchar as a variable. I'm going to count the number of characters that are processed in my range for loop. Notice that I'm accessing each element in that array A3 by reference. All right, so I'm going to get a reference to each one of the chars in A3 one at a time. And this trick, which you may or may not remember, in the ASCII character set, lowercase letters come after uppercase letters. And therefore, if I would like to convert these lowercase letters to uppercase letters in an ASCII machine, a trick that I can do is to compute the difference between little a and big A. Now, you probably don't have memorized that little a is 97 and big A is 65 in decimal terms. So the difference between the little a and the big A is 32. If I therefore take a lowercase letter and subtract 32, I get the corresponding uppercase letter, and because I'm doing this by reference, that's actually going to modify the character back in A3. And I'm then counting each character that I do this to. So when this upper for loop on references to elements is finished, and notice that because there's 2 statements here, I have had to use curly braces for this for loop, I then go back through A3 and I simply display each character. Now here's where the fact that I initialized A3 with a string literal creates perhaps a surprise for me, because remember there are 6 characters in that string literal, H-E-L-L-O and null. Now, what happens when you take a null and subtract 32 from it? Well, you get some bit pattern that may or may not correspond to some printable character on your machine. And it turns out that on my machine, when I display this character whose bit pattern is equal to 0 minus 32, what I get is this sort of hashed background block. You may have every so often see one of these things pop up in a terminal, and that means that there is a character there, but it's not a character within the standard printing range of characters on your system. So that's what I'm getting. I'm getting capital H, capital E, L, L, O, and then I'm getting this non-printing character represented as this gray box. Nchar, the number of characters that I counted, is 6. Okay, now I might be surprised by that if I had forgotten that initializing a character array from a string literal also throws in 1 characters for the null character at the end. Okay, so we've taken a look at an ordinary array of int, an ordinary array of double. Here we've got an ordinary Here we've got an ordinary array of char, A3, and now here's another value involving a vector of int. Nothing special happening here. This vector is initialized with the elements 9876, and in this range for loop we go through and print each one of them out. Here, S1 is a string object. I'm initializing it with a string literal hello. Now, for a string object, the string object does not have a null character at the end of the sequence of characters. And in this case, the size or the length of S1 is just going to be 5. Therefore, this black range for loop is only going to go through and access the 5 characters in S1 one by one, and my output will be H space, E space, L space, O space. And then I have a new line down here. Okay, I didn't get a space over here because whoops, too much yellow. I didn't get a space over here because I didn't ask for one, but here I am asking for a space following each character. Lastly, here I have P declared as a pointer to a char const containing the address of the little h at the beginning of this C-style string in static data. Remember that a string literal gets put into the static data area. This is an array of 6 chars, H, O, W, D, Y, null. P is not a container. Now, we know from what we've talked about the relationship between pointers and arrays in the past that pointers and array names are sort of interchangeable, and you can do subscripting on pointers, and you can do so-called address arithmetic on array names. But for the range for loop, you're only allowed to loop through containers where the size is known in advance. And although we could argue that the compiler ought to know the size here in advance, because P is a variable pointing at that string, the compiler can't be 100% certain without doing a bunch of code analysis that it doesn't bother to do, that P is pointing to a fixed size thing. So if we try to compile this code where we're using a range for loop on a pointer, we are going to get an error message. All right, well, that seems fair enough, so we can't use a range for loop on a pointer. Okay. Well, the bad news there, though, is that, remember, when you pass an array as an argument into a function, what that function actually receives is merely a pointer to the first element within the array. And consequently, if you have an array declared in your main function, let's say, and you pass the name of that array as an argument to some other function, let's say it's called ABC, then in the ABC file, if you attempt to use a range for loop to step through the array, well, in that function, the compiler no longer remembers that, oh, that pointer really is pointing in an array, and I ought to know what size that thing is. No, all that called function, the ABCD function, has the address of the first element, and information about how big that array is has been lost. That was only available back in the main function. So beware of attempting to use range for loops on pointers. Alrighty. So, now, one of the cool things about range for loops is that you can iterate through containers even when the container itself doesn't support integer subscripts. Now, it may not seem like a big deal that we can step through the elements in an array, we can step through the elements in a vector, we can step through the elements in a string, because we can subscript all of those things. We can say, array sub 0, vector sub 0, string sub 0. We can use integer subscripts. But it turns out that the set, which we'll get into in detail later on, does not have integer subscripts. A set is an ordered collection of values, but they are not subscripted, and yet nevertheless you can use a range for loop if you want to go through each of the items contained within a set. Okay, so that's the good news about the range for loop. It can iterate through any container, both arrays, string objects, and also all of the standard library containers like vector, set, list, double-ended queue, unordered set, and several others. But range for loops are not at all useful for dealing with C strings, okay, where the end of the C string is marked by a null character. The range for loop doesn't understand about looking for that null character at the end. And we can't use the range for loop to deal with anything that we have a pointer to. Also, if we have a container, we can't use a range for loop to step through just a portion of the container. If we're using if we are using a range for loop, that means that we want to go through each of the elements in the container one element at a time. So, how can we be a little more... Well, we'll be a little more flexible about that shortly when we talk about iterators. But meanwhile, let's take a look at some more functions that we can use for interacting with vector objects. All right, so here, continuing on in the same vector test code file, I've declared another empty vector of ints called IV6. Vectors grow and shrink very efficiently from the end. They don't grow and shrink efficiently from the front. And so we can put values at the back of a vector and take values from the back of the vector conveniently. We cannot use a similarly convenient function for doing things at the front of the vector. And precisely the reason that we are not provided with convenient functions for the front is because dealing with values at the front is slow. But in any case, so IV6 was empty, and now we're going to push a 9 onto the back. So at this point, IV6 does contain one element, which is 9. And then we push back a -3. So IV6 contains 9 followed by -3. And push back a 7. So IV6 now contains 3 elements, 9, -3, and 7. And as I said, there is no analogous push front member function. Okay, so if I now loop through IV6, I see that at this point it contains 9, -3, and 7. Another couple of convenient member functions that I can use are front and back, which don't modify the vector. They simply return the front element from the vector and the back element from the vector, respectively. So in this case, with IV6 containing 9, minus 3, and 7, front is going to be 9, back is going to be 7. To eliminate the final item, the final element from a vector, I use popback. And oddly, although, I mean, this makes sense in consistency with the other containers in the C++ standard library, but popback does not return any value. All it does is to eliminate the value from the end of the vector. So if you want to find out what the value at the back is and then get rid of it, you have to first use the .back member to return the value, and then the popback member to eliminate that value. So having eliminated the 7, if we now look at the back of the modified vector, the back at the modified vector now is minus 3. Okay, I can find out how big a vector is, that is how many elements it contains with the size member, and I can also test whether the vector is empty by using the empty member. Here I've used the bool alpha manipulator so that when I ask for IV6.empty, that's going to display as either true or false. In this case, because the IV6 still contains a 9 and a minus 3, empty returns false. Now, we can use subscripting with square brackets, and like an array, the default for vector subscripting is that there's no array bounds checking. So even though this vector container is supposed to be safer and more convenient than arrays, that doesn't mean it's required to be slow, and consequently it does not do array bounds checking by default. So it will, you can interact with it just as fast as you can with an ordinary array. And in fact, most of these functions here, like size and empty, are implemented as inline functions, so there isn't, for a lot of these things, even any function call overhead involved. All right, so here I'm using just an ordinary for loop with my index starting from 0 and going up to 1 less than the size. All right, so the current size is 2, so I is going to loop through 0 and then 1, and then the loop will be over. And I'm incrementing my counter in the change expression. And I'm just displaying IV6 sub I. The first time through that will display a 9, and the second time through that will display a 3, minus 3, pardon me, and then the loop will end. As an alternative to the square bracket, if you do want bounds checking to occur, you can use the at member function with the index as an argument. In this case, if the index is within bounds, that will return a value. But if the index is not within bounds, here I'm asking for the value at index 123, and of course the vector is only 2 values long, I get what's called an exception thrown, and the default when an exception is thrown is that your program dies. We will learn about exceptions and how to prevent exceptions from crashing our code a couple of lectures from now. Okay. Now, because all of the elements in a vector are in contiguous ascending memory locations, we can even use a pointer to an int to step through the items within an int vector. Here, p is my pointer to int that I'm using as my loop variable, and I'm initializing p with the address of IV5 sub 0. Now, we haven't seen IV5 for a while, so let's back up and find out what's in IV5. Okay, here's IV5 back here. And IV5 was initialized with a copy of IV. So IV5 contains 1, 2, 3, 9, 8, 7. All right, so there are 6 elements in IV5. And now let's see what's going on here. So I'm initializing P with the address of IV5 sub 0. And so that gives me the address of the first integer within IV5. And then I'm testing whether P is less than what I'm calling the end. Now, the end is actually one past the final address of an integer within the vector. All right, so the address of IV sub 5, try again. The address of IV5 sub 0, that's a pointer to the first int. And if I add 6, that would actually be a pointer to the 7th int. So it's actually a pointer that is one too far. And we're labeling that as the end pointer. So as long as P is less than the end pointer, we're going to display the value that P is pointing to, and then display a space, and then we'll increment P to point to the next int. And so this loop will work in the expected way, just as though IV5 were an ordinary array of int as opposed to a vector of int. And I'll end up displaying 1 space, 2 space, 3 space, and 987. Now, when you glance at this for loop, you might say, I get it. P is a pointer to an int, initialized with the address. Why can't I just see IV5 there? Oh, oops. IV5 is not the name of an array, so I can't just say IV5. IV5 is the name of a vector of int. So I do have to explicitly request the address of IV5 sub 0 in order to get the address of the initial element of that vector. Okay, I can eliminate all of the elements that a vector contains with .clear. And if I then check the size, I should get a 0. And if I ask whether the thing is empty, I should get a true. Okay. So that's several, not nearly all, but several of the member functions that you can use to interact with characteristics of and elements contained in a vector. Now, as a convenience, and sometimes a convenience bordering on necessity, and in fact, in the case of template functions and classes, it frankly is a necessity, you can use auto as a declaration for a variable. And when you use auto, the compiler will actually figure out for you the actual data type based on whatever expression you use to initialize the variable. So let's take a look at this first example. Here I'm saying auto v1 10. Now, because I've given 10 as my initialization, and because 10 is an int, that means the compiler will deduce that v1 is also an int. Okay, so I want to be clear here. It is not the case that v1 is some kind of flexible data type. The compiler analyzes this at compile time. The compiler sees that v1 is being initialized with a 10, and so the compiler says, oh, I get it, v1 is an int. On the other hand, if my initial value is a double, then the compiler will say, okay, this variable v2 is a double, and in the case of v3 here, I'm initializing v3 with the address of the h in high. Now high is going to be HI null stored in the static data area. And what I get back is the address of the little h. The little h is a const, so having analyzed all of that, the compiler is going to figure out that the data type of v3 is pointer to char const. Okay? I want to point out here that using auto does not relieve you of the burden of knowing what the data types of these variables are. You should know from looking at this statement that v3 is actually a pointer to a char const. It's just we're using auto here as a shorthand so that we don't have to type that mess. Okay? Failing to initialize an auto variable is an error, and so if we just said auto v4 semicolon, we would get a complaint from the compiler about that statement. Now, we often use auto in range for loops, basically just because we're too lazy to type data type names. So let me show you some examples. All right, so here I've got v7 is a vector of int, and v8 is a vector of double, and v9, this is a good one, v9 is a vector of pointers to character constants. And in my range for loops, I'm just saying for auto L, all right, since v7 is a container of ints, L here is going to be an int. In the next range for loop, since v8 is a container of double, EL is going to be a double. And in the third range for loop, since v9 is a vector of pointer to char const, EL will be a pointer to char const. As I said, you should know in your own mind that the first auto means int, the second auto means double, the third auto means pointer to char const, but you can relax and let the compiler worry about it rather than you having to type that stuff out. Notice how we initialized this vector of pointers to char const. We have 3 string literals here. So what we actually have here is the address of the little h in hi null, followed by the address of the little h in hello null, and finally the address of the little h in howdy null. So we've got 3 addresses of character constants, and those are in the vector v9. All right, next up we're going to take a look at something called an iterator. Now, an iterator basically allows you to use the same syntax that you would use to interact with a pointer, except it's got a more complex inner implementation, if you will, than ordinary pointers do. Basically, the idea of an iterator is to give you a familiar syntax that is a pointer-like syntax for stepping through the elements of a container. You're always allowed to step forward through the elements of a container. Some containers allow you also to step backwards, which is like decrementing a pointer. And iterators are used for things like insert and erase operations in the middles of containers or at the beginnings or ends of containers, and also can be used with a variety of standard algorithms that the standard library provides for doing things like copying values from one container to another, shuffling the values within a container, sorting them, replacing chunks of a container with other values. Altogether, there are 80 of these algorithms, so I'm not gonna name them all here. Okay. Now, in order to use an iterator, the type of the iterator is always going to be iterator that is a member of a certain class. All right? So the type of the iterator is part of the class that the iterator is associated with. If I have a vector of int, then the type of the iterator is iterator that is a member of the vector int class. So it'd be vector angle bracket int colon colon iterator. And as with arrays and pointers, we generally read these things from right to left. So let me show you specific examples. Actually, let me jump ahead for a minute and show you a specific example. Here we have a specific example of how to declare a vector of int iterator. Okay, all that stuff I've highlighted in yellow there on slide 20, that is a data type. And the variable being declared is it. I often lazily use it for iterator, just like I use I or j or k for an integer. So that declaration there says that it is an iterator that is a member of the vector of int class. And I could also have iterators that are members of the vector of double class, or members of the vector of pointer to character const class, or iterators that are member of the set of int class, and so on. All right, so that stuff highlighted in yellow and boxed in blue is what you type as the declaration, the data type, for an iterator object. All right, now let me back up a couple pages or a couple slides. The iterator that describes where the first element in the object is can be obtained with object.begin. And the element that is one sort of past the end of the container is object.end. Okay, so this is similar to the thing we did here with this pointer in this black for loop on slide 13. We set up pend to contain the address that is actually one beyond the end of my vector. And that's what we get from the .end member, is an iterator that is one beyond. Now, beyond doesn't necessarily mean after in memory, so I'm saying after in quotes here. But it does mean it's outside the bounds of the container. Okay, so let's see how we use begin and end. Now, begin is an iterator for the initial item in the container. End is beyond the final item in the container. It's not necessarily the case that begin is less than end in some numeric sense. We just don't know. That's an implementation detail hidden within the particular container that we're interacting with. All right, so the only operations that we can really use with iterators to compare them to begin or to end is we can test whether two iterators are exactly equal or are not equal or not the same. They don't refer. They're not iterators for the same element. All right. So in other words, here, diagrammatically, is how this would look in the case of a vector. Okay, so for a vector of t, we do know that the elements in a vector are in ascending contiguous memory locations. And so in the solid black outline here, these are the elements that this vector contains. If I say vector.begin, I get an iterator for the first element, and if I say vector.end, I get an iterator that is beyond the end of the elements in the vector. Okay, so vector.begin is the beginning, vector.end is beyond the end, just the next thing after the last one. As an alternative notation, which a lot of people prefer. I tend, I guess because I'm an old timer, I tend not to use this. Dot begin and dot end have been around forever. In recent versions of C++, you can say begin object as an alternative to object.begin, and likewise end object as an alternative to object.end. So let's look at actual code. All right. So here, this black for loop is essentially a repetition of the for loop that we looked at previously, and I'm using an ordinary pointer variable here. All right, so pn2 is a pointer to an int, and it contains the address of the initial element of IV4 plus 6. All right, so it's one beyond the end of IV4. Then I've got my loop variable here. P is a pointer to an int, initialized with the address of the initial value in the vector. And as long as P is not equal to pend, okay, here I've just changed what used to be a less than sign to a not equal to, but fortunately for us, the logic works out the same way. So if P has not yet reached pn2, we're going to display star P and then increment P. And then we'll do the test again. All right, so the only difference between this loop and the one that we looked at about 3 slides ago is that I've changed the less than to a not equal to. And now finally, on this bottom for loop, I am using a full-blown iterator with this long declaration. All right, so IT is my variable, and the data type of IT is iterator that belongs to the vector of int class. I'm setting IT to iv4.begin, and then I'm testing whether IT is not equal to iv.end, which is one beyond. Since IT is not yet iv.end, I'm going to display star IT. All right, notice that I'm using the star on my iterator, just like I used the star up here on my pointer. And that's going to display 1 and a space, okay, star IT and then a space. And then I'm going to increment my iterator, and that simply moves the iterator along to the next item in the vector. Well, IT is still not equal to iv4.end, so I display star of IT and a space, and that's going to be, whoops, that's going to be a 2 and a space, and so on. And so this loop will go through 6 times until finally, when we increment IT beyond the end, we'll discover that IT is now equal to iv4.end, and the loop will terminate. Okay, so an iterator mostly behaves like a pointer. I don't use a star when I declare the iterator, but I can compare the iterator for equality or inequality with some other iterator. In this case, I'm comparing IT with the end. I can also use star on the iterator to access the value that the iterator is, quote, pointing to, unquote. And I can increment the iterator, which will bump the iterator forward to the next element in the container. Okay, so, as I said, it's basically intended to mimic the behavior of pointers, but for more complex kinds of containers. Now, I expect that you are not going to want to have to type vector bracket int close bracket colon colon iterator very often. And so here is definitely a case where auto is really handy, because I can rewrite this loop that I wrote on slide 20 by just using auto instead. Okay, so the compiler realizes I'm declaring an object named IT here, and I'm initializing IT from iv4.begin. Well, iv4.begin returns an iterator that is a member of the vector of int class, and consequently the compiler will figure out, oh, that means that the real data type, the actual data type of IT must be vector that belongs, iterator that belongs to the vector of int class. All right, so I've just used auto here to save myself from all of this typing that I did on slide 20. And the remainder of the loop is the same. So I'm initializing IT with begin, testing whether IT is not the end. Since it's not the end, I'll display the value that IT is currently, quote, pointing to, unquote, and then increment IT, and so on. I do want to say one tidbit here about ++IT. It turns out that for ordinary pointers, for just plain old pointers to plain old data, it really doesn't matter in the change expression whether you pre-increment the pointer or post-increment the pointer. Because in the change expression itself, you are not using the value of the pointer for any purpose. All you're doing in the change expression is increasing the pointer by 1. Now, iterators are, it turns out, classes. And an iterator is a class of object. And iterators are more complicated than just plain pointers. And for efficiency reasons, which I may or may not get into, it turns out that it is more efficient to pre-increment an iterator than it is to post-increment an iterator. So we're doing pre-incrementing of iterators for efficiency. And since it doesn't matter for other kind of pointers, I'm going to recommend that from this point on in your life, if you're writing a for loop using either a pointer or an iterator, when you get to the change expression, just remember to use pre-increment. And in the case of iterators, that will be fractionally more efficient, and in the case of ordinary pointers, it won't make any difference. All right, well, here we're finally getting to the end of examples of vector stuff. This time I'm using the insert member, and the insert member does allow me to put values into a vector anywhere that I want. Now, it's intentionally a little bit less convenient to use than pushback to remind you that it's going to be less efficient than pushback. But the insert member takes an iterator as its first argument and a value as its second argument. So what this means here is that into IV4, I'm going to insert at the beginning a -4. And now I have -4 at the front of my vector, still followed by 1, 2, 3, 9, 8, 7, which is what I had before. Now I'm going to set up an iterator IT to, quote, point to, unquote, the beginning of IV4. And if I increment the iterator 2 times, that will actually bump the iterator forward. So now the iterator is pointing at, quote, pointing at, unquote, the 2. It started out, the iterator started out pointing at the -4. Then it was incremented to point to 1, and now it's incremented to point to 2. And pre-incrementing like this works for any kind of container. Works for vectors, works for sets, works for maps, works for lists, works for double-ended queues, on and on. And I can now use the erase member function to erase the item that this iterator is, quote, pointing to, unquote. And after I've done the IV4.erase of the 2 that iterator is pointing to, if I now display the vector, I see that the 2 is gone. Okay, so I have removed an item, an element from the middle of the vector. This also is an inefficient operation. I mean, it's as efficient as possible, but it's much less efficient than just adding values to the end and removing values from the end. Here we have another insert. the first argument is an iterator. Now, notice in my first insert, I only had one second argument, and so that was treated as the value to be inserted. But if I give two additional arguments, the second argument is treated as the number of values that I want to insert, and the third argument is the value that I want to insert 2 times. So here I'm inserting at the end. Actually, that means, before the end. That is, before one passed the end of the vector. Before one passed the end of the vector, I'm inserting 2 5s. And so now if I look at my vector, I'll see it contains -4, 1, 3, 9, 8, 7, 5, 5. All right. Now, as I said, any container allows you to do ordinary increments on iterators. For a vector class, you can even use pluskets to jump forward by multiple positions. So if I start out pointing at, quote, pointing at, unquote, the -4, and I jump that iterator ahead by 3, that modified iterator is now pointing at the 9. Okay, so we've looked at many things that you can do with vectors. We've talked about several ways of initializing them. We've talked about various ways of looping through them. We've seen that it's inexpensive to push values at the back and pop values from the back. You can also test to find out the front value and the back value, or you can find out the front value and the back value at any time. You can determine the size. You can determine whether the thing is empty. You can make the thing empty by clearing it. You can compare them for equality, inequality, ordering. And now here we've looked at iterators and inserting and erasing. There's even more things that you can do with vectors, but that's a reasonable overview. All right, so vector is just one example of the container classes. What is happening here? My highlighter is messed up. All right. The vector is one example of many containers that the C++ standard library contains. Originally, these things were developed outside of the standard as something called the Standard Template Library by some researchers at Hewlett-Packard, if I'm recalling correctly. And this so-called Standard Template Library was so important and so influential that it got pulled into the C++ standard library with just a couple of minor changes. So many people still refer to it as the STL, the Standard Template Library. Technically, it's not. Technically, the STL is the thing from Hewlett-Packard, and the thing in the C++ standard is just almost the same. Okay. Basically, there are 4 categories of containers. We have sequence containers like vector, and these have order n search times, just like a list has an order n search time. Then we have what are called associative or tree containers. The set that we're going to look at next is an example of a tree container. And just like our binary search tree, these things have order log n search. And we have unordered or hash table containers that have order 1 search. Okay? Furthermore, there are some so-called adapters that just slightly modify the interfaces, typically of underlying sequence containers. Stack queue and priority queue are the 3 adapters. Okay, then we have iterators that allow us to traverse back and forth through these containers, and there are about 80 standard algorithms for interacting with containers through iterators. We can do sorting, searching, shuffling, removing, inserting, copying, on and on. And this is about a 2-hour lecture that I'm not going to do right now. Okay. Each STL container, whether it's a vector or a set or a list or whatever, contains objects, okay? And the member functions that interact with containers make and manipulate and remove copies of objects. Therefore, the only kinds of objects that you can store into containers are objects that can be copied. What does that mean? Well, all of the fundamental data types, int, double, char, pointer to char, these kinds of things can be copied directly just using assignment. And so you can store those kinds of things into containers. You can also store higher level data types as long as those higher level data types have a public copy constructor. All right, so you could not store employees in a vector because you cannot make a copy, that is, you cannot make a clone of an employee. So, things that don't have public copy constructors can't go into containers. Likewise, references can't go into containers. You cannot have a vector of references to ints or a vector of references to employees. Fortunately, though, a pointer can be copied easily. And so, although you can't have a reference in a container, you can have a pointer in a container. And although you can't make a copy of an employee object, you can make as many copies as you wish of the address of an employee. Okay? So if we want to store non-copyable things into containers in some fashion, we do that by storing pointers to those things. We cannot do that by using references to those things. All right, so that's a couple of picky limitations to be aware of about what you can store in containers like vectors and sets and lists. All right, well, finally, we're going to wrap up by looking at a few things that we can do with sets. A set is useful in and of itself. I also want to use it in contrast to the vector that we just got done talking about. Okay, a set stores single values, although these single values can be structures or copyable class objects, and no duplicates are allowed. All right, so a set only has unique values. And a set is organized as a tree. It's what's called an associative container. By default, the items stored or the elements stored into a set are put into ascending order according to whatever the less than operation is for the values that you're putting into a set. Now, if you have a class where the objects are copyable, but the objects cannot be compared to see whether one object is less than another, then you cannot put these objects into a set. If you try to put these objects into a set, you'll get yelled at that there's no way of doing a less than test. You can certainly put those things into a vector, but then you can't determine, you don't have any obvious way of knowing whether you've accidentally put duplicates into a vector, because a vector doesn't complain about duplicates. We can modify the sort order, and we'll see how to do that later. We do have assignment, equality and inequality in relational operations. Less than for a set is a bit like less than for a vector. If the element types of the two sets can be compared, so for example, you have two sets of ints or two sets of doubles, or one set of ints and another set of doubles where the elements can actually be compared, then if the lowest element in one set is less than the lowest element in another set, then that original set whose lowest element is lower is considered less than the other set. I hope that made any sense at all. We do not, in the set, have a concept of subscripting. So we cannot use the subscript operator on a set. But fortunately, we can use iterators to traverse through a set using plus plus to go forward. And in fact, we can also use minus minus in a set to go backward. And we have a variety of members allowing us to do things like inserting values into a set, testing whether a value is in a set, removing values from a set, and so forth. So let's take a look at some of these. All right, now here is my settest.cpp file. This is also in the example code files that you can look at. And I've got a bunch of headers being pulled in here. IO streams, I can use cout, C standard lib, so I can generate random numbers with rand, vector, string, and set. And here I only have room for for one thing in main, and I'm declaring si1 as a set of ints, and this is empty. All right, so it is a properly initialized empty set. Now, here si2 is a set of int. Okay, and si2 is being initialized, and here I've given an initialization list of a bunch of integers, 2, 3, 1, 6, 5, 6, 6, 6. Notice that the 6 is repeated, but duplicates are not allowed. I won't get an error from the compiler. I won't get an error at runtime, but I will discover after I've done this initialization and I look at the contents of si2, pardon me. All right, so after I've created and initialized si2 and I loop through it and display the element values, I'll see that the element values are contained in ascending order, 1, 2, 3, 5, 6, with no duplicates. Next up, I have iv1, which is an integer vector, and I've got 828783, but of course that gets reduced to 2378 in ascending order with no duplicates. Notice here, oops, I misspoke. iv1 is not a vector. iv1 is an integer vector. All right, we'll try that a third time. iv1 is not a set of int. iv1 is a vector of int, and it is happy to contain duplicates. So iv1 is a vector of 6 ints, 8, 2, 8, 7, 8, 3. si3 is a set of ints, and here I want to illustrate yet another way of initializing the elements of a container. It turns out that in between parentheses, you can specify 2 iterators, and the object that you're declaring and initializing will automatically be initialized from, in this case, this other container with all of the values starting from the beginning and going up to just less than the end. All right, so we are using the values 828783, that is all the values in iv1 from the beginning up to just before the end. And now the duplicates will be rejected and they will be put in ascending order so that when I display the set si3, I will see that si3 contains 2378. All right. In this green example, I'm creating a string object, st1, and I'm initializing that string object from this is a test. So that's going to be, what, 5, 10? That's going to be 14 characters long. And I can create a set of those characters called SC1. I can traverse through the items in a string object also by using the begin and end iterators. Okay? So the iterators are going to treat the string object as being a sequence of individual char values. SC1 is declared as a set of char, and it's going to be initialized from this sequence, T, H, I, S, space, I, S, space, A, space, blah, blah. And when that sequence of individual characters is used to initialize a set of characters, when I then look at the contents of that set, what I'm going to see is, now, all right, so, all right, so it wouldn't let me quite highlight the way I want, but notice that there are 3 spaces in this string. Spaces around the is and spaces and another space after the a. So space does actually count as one of the chars in the set. And it turns out that the space in the ASCII character set comes ahead of all these other letters. So when I loop through the set of char and display the characters one by one, I get space A, E, H, I, S, T. All right, so those characters are in ascending order, and they come out separated by space characters because I've asked for a space character in between each one. So, good things to know that a string is iterable using the begin and end iterators. Here, I'm creating a set of string objects. This is called SST1, set of strings. Set of, SST for set of strings, number 1. And I'm initializing each of the string objects in this set of string objects by using a string literal. Now, as we've seen, you can use a string literal to initialize a string object, but that does not include the final null character. So the string objects in here are going to be the 4-character THIS, the 2-character IS, the 1-character A, etc., etc. Since duplicates are disallowed and the strings are stored in order, when I then loop through the elements of this set of strings, what I see is that there are 5 strings in this set. Is, only, test, and this. Okay, so that's the string objects in ascending ASCII order. Here in the blue code, I'm setting up SRI as an empty in a set of integers. And now I'm going to generate random numbers and insert those random numbers into the set. So that everybody gets the same values, I'm starting my random number sequence by setting the seed to 0. And I'm going to use an ordinary for loop to loop through and add 100, or loop through and insert 100 values into the set of random integers. Now, all of the random integers that I'm inserting are going to be in the range from 0 to 199. And I'm going to do 100 inserts. Now, it's likely when I ask for a random number and take its remainder after division by 200, it's likely that I'm going to get some duplicates. Okay, so among these 100 random values that I'm drawing, I'm likely to have several duplicates. So it's unlikely that SRI, when I'm finished, will actually contain 100 values. It could contain at most 100 values if I happen to get 100 different random values, but that seems quite unlikely. And in fact, since I set my seed to 0, if I now turn on bool alpha and ask whether SRI is empty, well, fortunately, it's not empty. It does have some things in it, but when I then ask for the size, what I'm told here is in this particular sequence of random values, only 74 unique values were stored into the set. So I must have gotten 26 duplicate values to those 74 values among the 100 values that I drew. Okay. Now, here in the red for loop, I'm attempting to find 10 random values. I'm going to generate 10 random values in the range from 0 to 199. And I'm going to search, well, maybe I should have said find, since that's the name of the function. I'm going to find, or attempt to find, that random variable, which I've stored into the variable k. I'm going to attempt to find that random variable, that random number, in my set. One of two things can happen now. If the value k, whatever it is, does exist within the set, what I will get back is an iterator for that particular value in the set. But if the value does not exist within the set, what I get back as my iterator is the end value, which is outside of the set. Remember that end is just outside of the set. We can think of that. All right, so 10 times in my loop, I'm going to generate a random number. Then I'm going to try to find that random number in the set. If the iterator is end, if the iterator is not end, then I can display the message that SRI contains, and here I'm using star on the iterator to confirm what that value is that I found. On the other hand, if the iterator I got is the end, that means that SRA contains no value k, whatever the random value k was. And when I run this loop 10 times, my recollection is that of these 10, I find 2 or 3 and don't find 6 or 7. You can test it to discover for yourself. Another way that I can check for values in a set is to count the number of times that a value exists. Now, for a set, since a set only contains unique values, I can basically use this as a direct alternative to find, because if I ask for the count of the value 9 and I get back a 0, that means 9 is not in the set. If I ask for a count of the value 9 and I get back a 1, that means that the 9 is in the set. Okay? Now, counting, I guess, is, fractionally less efficient than finding, although since a set contains unique values, it's not clear that it works out any different for a set. All right. Now, to find out the lowest value in a set, I can simply ask for the iterator sri.begin, and that is going to give me back an iterator for the lowest value in the set. So if I apply a star to that iterator, I will get the value of that lowest element in the set. And in my case, when I ran this test code, I got told, okay, the lowest value in this set of up to 100 random numbers turns out to be 0. I did actually generate a 0, so 0 is the lowest value in that set. I'd also like to know the highest value in the set. And the highest value is trickier to figure out because I can ask for sri.end, but sri.end is outside the set, and I need to look at the last value inside the set. Well, lucky for me, with a set iterator, I can count backwards as well as forwards. And so by going to the end and then backing up 1, that allows me to get to the final value in the set. And if I then use star on that iterator that is just one prior to the end, I'll see that in my case, when I ran this, the highest value in my set was 197. All right, so there's a ton more that you can do with sets, but I wanted to show you some of the ways of initializing sets, also how to use iterators, how to use iterators in initializations of not only sets but various other kinds of containers, finding and counting and so forth. And finally, we are at the conclusion of lecture 24. Okay.